Brian, for the introduction, and thanks, Ross, for the invite. So today I'm going to talk a little bit about how domain-informed, that is the scientific domain-informed machine learning is sort of changing several aspects of scientific discovery. So what is machine learning? Let me begin with that. So machine learning is sort of, it's a technology, or it's a field born from ambitious goal of artificial intelligence. Okay, so historically there are two opposed views, or two different types of approaches to artificial intelligence. The first one is symbolic programming, which is sort of mind-inspired, top-down, where domain experts looked at how to solve a problem and encapsulated that knowledge into a set of rules. And those rules become computer code, and they sort of designed expert system to solve problems. The opposing, or the other way to look at designing artificial intelligence system is machine learning, which is now gaining a lot of attention in different areas, not only in science, but also in the commercial world. So this is more brain-inspired. So think about, okay, so brain is composed of neurons, right? And neurons, they sort of connected to each other, and by just doing activation, we sort of have intelligence that is sort of emerging, right? So this is the sort of this brain-inspired way of looking at designing AI system. So this is more bottom up. Here, instead of set of rules like the expert system, here we design training systems. Okay? The training systems take data and then produce a model, which will be then used for solving different types of problems. Okay, so as I said, artificial intelligence is sort of a very broad idea, a set of concepts with which we want to design intelligent system to solve problems without explicitly telling how to solve the problem. Okay? Machine learning is a promising approach. It's a set of ideas, algorithms, methods, concepts to build such type of system. Deep learning, which is sort of the current state-of-the-art methods, belong to this class, deep learning, where you take different types of models and stack them in different ways, or you combine them in a much deeper way to model really complicated functions. Okay, so that's the class of deep learning. And deep neural nets is a particular class of method, it's a particular way, as a subset of deep learning, which sort of loosely inspires how brain is connected. Like with the neurons, so you have an equivalent of that called computational units, which are sort of connected in a hierarchical way to solve different types of problems. Machine learning is not a magic. It resembles a lot from how we learn in real world. Okay, so machine learning methods, you can say, you can broadly classify them as 4 different classes. The first one is supervised learning. This is pretty similar to how we humans learn from our parents, from our mentors, and our supervisors, and so on and so forth. Someone is there to supervise us, and we learn from that. Okay, so the supervised learning algorithms follow the same principle. Unsupervised learning is how we understand the world without someone explicitly telling what it is. For example, when we were kids, we know a lot about our world. Our world is made up of trees. It has shapes and symmetries and so on and so forth. No one is there to sort of come and tell us like what that is. Of course, someone has to come and say, this is a table, this is a chair. But even before that, we sort of understand what they are, right? So unsupervised learning basically belongs to that class of learning. Semi-supervised learning is sort of a mix between supervised and unsupervised learning, where we know things from the supervision and things from unsupervised way of learning, and then we combine them to solve the problem. And finally, reinforcement learning is a class of methods where sort of, how we learn by doing experiments, right? So we experiment with something, we learn from that, and then we use that as a feedback to do something else. So reinforcement learning, again, it belongs to that class of learning. Okay, so let's first focus on supervised learning. An example is shown here. So where you have set of inputs here, it's a cat image, dog image, and outputs, which are sort of labels, which says what is a cat, what is a dog, and what is a horse, right? So the very fact that we have to give these labels, right? This is a cat, this is a dog, makes this as a supervised learning. So without that, the machine does not understand how to associate these two, the input and the output. Okay? So once you give the input and output, it undergoes a process called training. And then it produces a model. With that model, you can give a new image and then predict what that image is. Okay? So the state-of-the-art algorithm to do that is deep neural nets, in particular deep convolution neural nets. A picture is shown here. So the input, so it has several layers, as you can see. So the input layer is the layer which receives the images. And then it has a number of hidden layers, right? And each layer is basically a computational unit, which is sort of characterized or parameterized by weights. And those are the weights you learn. And how you learn? So there are two phases. So first is forward propagation, in which you give the images, and then you pass it through the neural net, and then you know the labels, right? So that's where the supervised learning is coming from. And then you predict what that particular image is. Let's say if it is a cat, but you predict it's a horse, and there is this difference, and you basically take the difference and backpropagate and try to adjust the parameters of the neural net in such a way that it minimizes that error. Okay? So what the neural nets learn is, an example is shown here. So at the lower level of the neural net, what you see here are the edges. Okay? And at the higher levels, what you see is that it learns texture, so it puts all the edges into textures, patterns, and the paths, and finally objects. So this is what the neural network is learning. It tries to extract basic features, and then take those features and then construct them in a hierarchical way to do the high-level classification. Okay. So whatever I said is not new, even though they are state-of-the-art. The methods existed from 1980s. So what has changed is the following. So what you see in the graph, in the x-axis is the scale, starting from data size and model size, bigger models, and y-axis is the accuracy. So neural nets shown in the blue, and the green is other approaches. Before, we didn't have a lot of data, and we cannot build bigger models because we don't have compute power to train such big models. Now, we have a lot more compute power, and because of that, and also we have a lot of data. Because of that, we can build bigger models, and we can train them in a relatively shorter time. Okay? So that's the secret sauce of the recent emergence of these deep learning methods. Okay, so such a kind of supervised learning has literally changing many fields in the industry, and also in several scientific fields, starting from image analysis in different disciplines, speech, language, autonomous driving, healthcare, and finance as well. What this means for scientific machine learning, that is, the machine learning in scientific domain. Okay? So what are the challenges? The first challenge, because we don't have one particular scientific field that we care about, we have many different fields, and because of that, the data that we have to deal with is heterogeneous. For example, the data available can be broadly classified into two. One is regular domain, where you have spatial and temporal, like the spatial data is images, and temporal is, let's say, time series. And you move to irregular domain, you have many, starting from tabular data, graphs, manifolds, and point clouds, and so on and so forth. So there's no single type of data that is sort of produced, even if you take one single scientific discipline. Okay? And then, from the methodological perspective, there are many other challenges as well. Okay? So first, for the regular domains, we have reasonably good methods. Now we have to understand and try to apply that to scientific data. But then irregular domains, we don't have a lot of methods. We need to develop new machine learning methods. And often we don't have a lot of data. If you are a Facebook or if you're Google, you have a lot of data to play with. In scientific settings, each experiment is expensive. And we don't have millions of cats and dog images or equivalent of millions of cats and dog images in a scientific setting to do really large-scale model training. Okay? Physical models, domain constraints. So we need to make sure the model that we build is robust enough, how to incorporate the knowledge that we already have, and how to impose physical constraints and so on and so forth. That's a challenge as well. Model development takes a lot of time. Machine learning is not a push-button technology. It has a lot of trial and error, and it takes a lot of time to develop really good models. And scalability, as we all know, this takes a lot of time. So one way to speed up building models is to use big supercomputers to speed up the model training. Okay, so next I'm going to sort of talk about some case studies in which we try to address some of these problems. So the first one is the 3D atom probe tomography. So it's basically a process in which it's a characterization process for a range of material systems. So you prepare a sample, scientists prepare a sample in a needle shape, and then they send laser pulse, and then they remove the atom one by one, layer by layer, okay, in the form of ion, and that is passed through the counter electrode, which is then passed through the position-sensitive detector. So what you get as a result is the three-dimensional mapping of the atom distribution, and that distribution is sort of a point cloud. Okay, so this point cloud can be used to do several different type of analysis. So one of them being this one. Okay, so what you see here is the same point cloud. Okay, from the experiment. So it's a different combination of the metals: cobalt, aluminum, chromium, nickel, and tungsten. So this region means that you have several combinations, but here you see only two of them. So what are the important things about this one is the thing called proximity histogram. So once you identify this interface, then you just go and traverse this area and then find what is the distribution of this particular atom from this interface. So that is what, so this is the distance, 0, and this is the interface, and if you move up if you move down here, then that's where you have higher density. Okay, so identifying the interface, the interface thickness is critical to analyze this point cloud data. Okay, so the current practice, user usually come up with some sort of isoconcentration surfaces and then some particular values, and then this is sort of a manual process to identify the interface thickness. Okay, so how about doing deep learning on that, right? So it's an edge detection problem, and edge detection is a computer vision problem, and there are several deep learning methods for doing those type of edge detection. Okay, so having said that, edge detection is very subjective, and it is a sort of a hierarchical process in which you combine different edges in a different way and then come up with the correct edge. So the method that we used is shown in the figure. So this is not a pure like convolution neural net where you give the image and try to reconstruct the edges. So what you have here as an input, you have the original point cloud, or in this example, you have a horse and you want to identify the edges. So you give a lot of examples of this horse as an input and the ground truth, the edges as the output, and you want to make the neural net learn this mapping between this image to this image. So the way that you train the system is as following. Each convolution error, you force the neural net to sort of reconstruct the edges here. So it's not end-to-end, but in between each convolution layer, you force the network to sort of build the edges, right? So this is similar, let's say, if we are building some convolutional neural net or other neural net for physical models, we can force the intermediate layers to sort of satisfy certain properties or follow some physical constraints and so on and so forth. So that is the sort of the analogy, okay? So we can do this, and then we can train the system to identify the edges. But what is the problem? We don't have a lot of data to train the system, okay? So 3D atom tomography, we can do few experiments, we can get some data, but it is not in thousands, right? So what we did is the thing called transfer learning. So we have to deal with the limited data. How we can do transfer learning is we took the real world images, right? And then do the edge detection, apply the algorithm to learn to do the edge detection. And then we use the same model with few modifications and then use the 3D atom probe tomography to do the edge detection. And from that, we can build these edges. And we can go and do this on 3 dimensions, x slice, y slice, and z slice. And then we can do this reconstruction, which is a segment precipitate, and done with it. So we don't need to have to collect a lot of 3D atom probe tomography data with the interface edges. So this is how we solve or we address this problem of limited data. We did similar thing with image enhancements in the compressed sensing. So scientific simulations produces a lot of data, a lot of high quality data, but the key challenge there is how to move that data from the compute node to all the way to the storage node. So one way is to use JPEG compression, which is a lossy compression, where you compress the data in the node where it produced, and then you move the data to the storage. The problem, you will have compression artifacts as shown here. So this is a compressed image where you have this sort of artifact. The idea here is to use deep learning to sort of remove these artifacts introduced by compression. How to do that? We can take a lot of images of this one, the images with artifact and images without artifact, and train a deep learning system to do the mapping from, okay, given an image with compression artifact, how you want to get the pure image without the compression artifact. Okay? So we did that, and then is it specific to climate simulation? No, because the process of removing the compression artifacts is sort of generalizable, right? And that's the property that we exploit, and then we also take this model and apply to kinetic fusion to solve the same problem. Okay, so we don't need to retrain this model for a different set of simulation if it is using compressed sensing. Okay, so why this transfer learning works, or in general, why convolutional neural net works? The secret sauce here is the Euclidean property of the data. Okay, what is that? So if you take images, right? So images can be sort of thought, you can see images as a pixel sample from a regular grid, right? So whatever the images we see, we can do that in a two-dimensional grid, and they can be considered as pixel samples from that grid. Okay, so because of that property, we can then do this operation of convolution where you sort of slide over that grid and extract features, and then you can construct those features little by little, right? And also it exploits the property of spatial correlation, means that given one pixel in any image, there is a high chance that pixel is correlated to the nearby images, right? So that's the Euclidean nature of this data. Because of that, we can then design convolutional neural nets and extract features and have really good performance provided enough training data. Okay, so what if the data is non-Euclidean? What if the data is not an image? So I'm going to talk about another project in which we deal with the non-Euclidean data. So mobility it's a part of this project, mobility design and planning project, where we want to predict the traffic flow using machine learning. How can we do this? If we ignore the non-Euclidean property of the data, okay, so we can take the images, we can look at the image of the traffic, and it's all red. Can we do convolutional neural net on top of it? And done with it, because it's an image and we see this image, right? No. Why? Because the spatial correlation is a little different. Can I explain that with this example? Okay, so this is not super visible, but what you will see here is two roads. One go into the city, one getting out of the city. Okay, so this is one part of the road, this is another part of the road. Okay, even though these 2 points are near to each other, they are completely different, because this one traffic is going in and this one traffic is going out. On the other hand, this point is far away from this point, but this is correlated to this one because they are on the same side of the road, right? So the spatial correlation does not hold. So you cannot just convert anything into images and say, okay, I'm going to apply convolution on top of them. Okay, so how to take that into account? And then you have this problem-specific complexities such as non-stationarity, because the time series, the variance in the traffic differs from from road to road based on the time, and so on and so forth. Okay? Okay, so how to deal with this? We use recurrent neural net. So let's first focus on how to tackle the temporal aspect of the problem, because it's a time series. Traffic flow is a time series, right? So we use recurrent neural net, okay? And the recurrent neural net is basically saying that it takes a sequential input like xt minus 1, xt plus 1, okay? And it wants to predict something here, like ot minus 1 ot and ot plus 1. So at a time t xt given an input, the output ot not only depends on xt, but also depends on what happened at xt minus 1. And recurrent neural net exactly captures this. How? So what it has is a sort of hidden state st, which is computed as some matrix, weight matrix w times the previous hidden state st minus 1, and the u weight matrix multiplied by xt. And then it passes through some nonlinearity, and you have this hidden state st. So what this means is that the hidden state st contains information about what has happened in the past. And that information is combined with my current time step t to predict what will happen given this xt time, what happens at the xt, what happens when you give the input xt. Okay? All right, so how do you train this? You do the forward pass, and then you compute the gradient. So gradient is nothing but you look at the difference between your observed value and the predicted value, and then you compute the loss, and then you take that loss and you go and see how I can nudge the parameters in u, w, and v so that I can minimize that error. Okay? So this is simple because ot plus 1 depends only on v, whereas this gradients depends on these gradients as well. So you have to take, so these gradients depends on these other gradients as well. So it's undergrad calculus, so I'm not going to go deep into that, and it is not needed for now. So all you need to understand is that there is a mathematical formalism and formula that can allow us to go and nudge w, v, and u parameters to minimize the error. Okay? All right. So we are done. Okay. So what we want to do actually is given the traffic up to time xt, we want to predict the next few time steps, right? Next 30 minutes or 1 hour. So the way that we design the neural net is you have RNN cells, and you get the prediction of xt plus 1, and you give that as an input. And then, because this is a predicted input, and you give that as an input to the next cell to get the next prediction. Okay? Because you want to do sequence of predictions, not one prediction. Okay, great. So now we are done with how to tackle the issue of time series. Now we are coming into the real non-Euclidean nature of the data, where the transportation network can be seen as a graph, right? And we say, let's say, sensors that measures the traffic flow, and E, the edges of the roads and the distance between them. Okay, so A is the weighted adjacency matrix that says how my point in the road A is connected to another point in the B. So how the traffic flows. So basically, adjacency matrix tells or defines the connectivity between different nodes. Okay, and then there is some sort of smoothness that you define and use that smoothness so instead of the weighted adjacency matrix. Okay, so so what we want to find is the following. So we have a graph, and the graph is a time series, right? So you have a traffic that flows through this graph, and we want to find a function h dot, right? That's a function that we want to learn that can give us the next state of the graph, not only the next state, but the next state, condition on this next state, we want to find the next state as well, and so on and so forth. So how we can do this is using diffusion process-based convolution. So diffusion process can model traffic from a domain perspective, right? So diffusion is a process where things move from higher concentration to lower concentration. So in the case of traffic, you have a high point with a lot of cars, and that moves to an area with a lower car count. So what we want to find is exactly that. So you have this state. This is the final state. This can be represented as, okay, so here is my initial state, And here is my density of the cars. And in the next step, cars move to this state, this state, this state, defined by the connectivity, which is defined as a part of the input, and so on and so forth. Then this basically what we want to learn is theta 0, theta 1, theta 2, and theta k. And that will be learned using the data that we provide. Okay? So, and you can basically define this as a transition matrix. So this is for the diffusion, and this is for the reverse diffusion. And what this means is the reverse diffusion basically handles like when there is an accident, there is some sort of backlog, right? So that is a process that you want to capture. So basically these two transition matrices and theta k and theta k for each one of them are the parameters that you want to learn. Okay, so great. So you remember the RNN equation? So the RNN cell with a single one. So if you want to do it for the whole graph, all we need to do is instead of the W, U, and V matrix, we are going to put the graph convolution or the diffusion convolution matrices W star, U star, and V star. That's it. Okay. So we did this on, we tested that approach on this I-210 road with 80 east loop detectors and 80 west loop detectors. And these are the prediction results. And the results are pretty amazing. And what you see here is for one sensor location, loop detector location. This is the prediction on the speed. It pretty much gets, the horizon is for 60 minutes. It pretty much gets the traffic speed, the average speed. This is, again, for speed for a different location, but with a different sort of variance. And overall, so we have 160 detectors, and mean absolute error on all of them is less than 4 on speed. So on an average, it was doing really well. Similarly, for the flow, that is the number of vehicles that passes through that particular location, we have pretty good results, and the mean absolute error is less than 40. So remember, the scale is in the order of thousands. Okay, great. So now I'm going to focus a little bit on reinforcement learning. So this is a sort of method in which an agent performs an action and gets a reward for that action. And based on that, the agent performs the next set of action. So the reward basically determines how this agent will do further actions. Okay, so such type of approaches sort of changed several things. Especially this is a AlphaGo system designed by Google DeepMind, which beats Lee Sedol, who is like 18 times world champion in the game of Go, because game of Go is much more complicated than game of chess. And computers, before this approach came in, computers, if you are an average player, you can beat the computer. And using reinforcement learning, you can design really powerful system. Okay, so let me go back and sort of discuss this approach with a simple example of Pong. Okay, so you all know this game Pong, and if you want to teach an agent to learn to play Pong, how we can do that? So the supervised learning approach is, okay, we take these images and then we put a neural net, and then we say there is a human gamer who plays, and given a frame, he moves up, and another frame he moves down. So we record a lot of these images and give this to supervised learning approach. And what you get as a result is a system that, given an image, it can learn to move up or down. Okay, so that's the supervised learning approach. What is the problem? First of all, for each possible set or possible images, you need to give a label. So essentially, you need to have a lot of training data for this simple game. And at the end of the day, if the human gamer is a mediocre player, the system will be mediocre as well, right? So we want to design a system that can play better than humans. So how to do that? So here is the reinforcement learning formulation comes in. So instead of telling the agent what is good and what is, so for a given image, whether you want to move up or down, let the agent play the game, okay? And then give the score as the reward to the agent. And the agent in the beginning, it will make a lot of mistakes. It does not know how to move and so on and so forth, but it will slowly start learning using the reward. And then it slowly starts getting better at it. Okay? So here is what happens. So the approach that we use for learning or to design such system is called policy gradient method. And the policy gradient method works as follows. So you have this game, let's say up, down, and then you win, and then you play that number of times. So each time you win, sometimes you lose, and what you have is you do forward propagation and backward propagation, but in a different way. So you give an image, and you get the log probabilities. So probabilities is basically the action, whether you want to move up or down. And then you have a sampled action. And if your reward is negative, you go and punish the agent for doing that. Okay? If you get a reward of positive reward, then you go and favor that agent. Okay? Favor the sequence of actions. The problem here is the following. Okay? What happens is so you have a winning sequence, and you have a losing sequence. Let's say all these are good, but only this one, the up is bad. So it just missed that. Instead of moving down, it moved up, and you lose it. So the first challenge is it's a sparse reward. So you don't know whether the up is a good move, this one is a good move, this one is a good move. All you know is after making a sequence of moves, you know whether you are going to win or lose. So this is a sparse reward problem. Okay, you get reward only at the end, not for all your actions. And also because of that, there is this issue of sample inefficiency, right? You need to have a lot of games to sort of learn or to learn which moves are better. So this is called the credit assignment problem. Okay, if you win, how are you going to assign the credit to all the sequences or all the decisions that you made previously? Okay, so to address that, several methods have been proposed. I'm going to talk about the high-level idea, the first one being the score function gradient estimator. So basically, you have a score function f of x, which is the reward. Like, when you win, you have +1. When you lose, -1. And what you have here is some expected value x. You sample from some neural network, and that can be characterized as probability distribution, px of theta. Okay? And what we want is a gradient on that score function. So if we know the gradient, then we can use the gradient to go and adjust and nudge the parameters of the neural network that we use. Okay. So this gradient is hard to compute, but with some mathematical transformations, what we can get is this value, where your expected value of this x is basically saying that you take the score function and take the gradient of the sample and multiply that, and you do that for a number of samples, and that will be used to nudge your parameters to make better decisions. Okay? In other words, this is what happens. So let's say you have a distribution p of x, and you have the samples, which are shown here, and the gradient theta log p of x. Okay? What you have as the next one is the score function. Everywhere it's -1, and there are some areas with +1. So you make the decision based on the samples, and you get some reward. And what you want to do is using this gradient, so if you have good scores in the part of the space, you use those gradients to sort of move or nudge this distribution in such a way that it generates better samples or better actions for the next set of games. Okay, so the one that we use is policy gradient method. Again, the simplified version is shown here. If you look at the equation, it's the same. It's the expected value, and it uses something called advantage function, A of t. And log p of x of t is basically the actions that you take from the neural network. So what it is doing here is the following. The advantage function is basically your agent playing games and collecting the rewards. So let's say it plays several games, and then it collects some rewards, minus the baseline estimate. And the baseline estimate is nothing but another neural network that is learning how this agent is performing, right? So the agent has seen several states, and there is one neural net that is basically trying to get better in playing the game. But there is another neural net that predicts on an average what the reward or the expected reward of this neural net should be. And if this guy is doing better than the expected performance, then it is good. So you go and nudge the parameters and favors the same set of actions. If it is not, then nudge the parameters in such a way that you move away from what you are doing. Okay? So this is called actor-critic method. So there is two neural nets. One is actor, another one is critic, and the actor is playing the game, and the critic is learning how well this actor is doing. And using the difference, you go and nudge the parameters to move your distribution. Okay? So what we did here is the following. We used recurrent neural, we use reinforcement learning to automatically construct neural nets, because constructing neural nets is a time-consuming process. So how we do that is shown here. So we have cell and block and the structure. So cell, block consists of cells, and the structure consists of number of blocks. And we use a recurrent neural net, an agent now. This guy is the agent, and that makes decisions, and it will construct the neural net as shown here. So once it constructs the neural net, then it can go and evaluate this neural net for the given data set and can get the reward. And then once you get the reward, which is the accuracy, and there is this is the actor, and there is a critic who will see how well this actor is doing, then you can use both of them to make the system to generate better architectures. Okay, so you can build really complex architectures with that, and then we scale that method on big supercomputers so that we can reduce the time in generating the recurrent neural nets. So application performance modeling is something that we do. Applications running on supercomputers, it's not deterministic because of different reasons, one being the shared resources, interconnect and file system, background traffic, and network inference. So we have historical data, and we want to build predictive models. So we use reinforcement learning agents to generate those models, and this is the network architecture it came up with, and this is the accuracy, which is pretty good, 0.9 in correlation coefficient. Okay, great. So here is a fun fact. This is a supercomputer that is developing a model to predict its own behavior. So this is another exercise which we did with weather research forecasting, where we want to build surrogate model for planetary boundary layers. And this is the network it came up with. And here it has to predict different metrics for the different levels of the atmosphere. And this is on the level 0, very good correlation coefficient. At the higher levels, the correlation coefficient decreases, but that's for a reason, because at the higher levels, we need to take into account the temporal aspect of the data, but this is expected. So we are working on how to improve that. So this is a study on engine drive cycle modeling. Again, input spark timing, engine, and so on and so forth, and the multiple outputs, temporal variations of the pressure, temperature, and so on, other metrics. And this is the neural net that the reinforcement learning agent came up with. And here is a correlation coefficient, again, above 0.99 for all the metrics. Okay, great. So I'm coming to an end where if intelligence is a cake, right? So what we are all doing, or majority of us doing now, is supervised learning, which is sort of the icing on a cake. But the cake actually is the unsupervised learning and supervised learning. I want to give a couple of examples before concluding the talk. So this is an example of an unsupervised learning without explicitly telling celebrities. We just, the guys from NVIDIA took celebrity images and let the neural network learn without telling how the celebrities look like. And the neural net learns how the celebrities look like, and then it started generating celebrity looking like images. And all these are not real people. These are all artificially generated images. Okay? And these are pretty good. They look like celebrities, right? So from this you can say, oh yeah, these are not celebrities. But so what this means for science is let's imagine if we can take set of all known molecules and let neural network learn how molecules look like, molecular structure. Molecular structure means atoms, bonds, and so on and so forth. If the neural network can learn that, then we don't need to we don't need to collect a lot of data to do predictions and so on and so forth. So this is about teaching neural net what the domain is about, what the data it is going to see. So once we do that, then we can do sort of this inverse mapping. So usually we go from this, the chemical space to the functional space, right? So chemical structures to the properties. But what we really want to do is, a scientist comes and say, I want a property with metric A, metric B, metric C within this range, and we should be able to generate that immediately, right? So that's the sort of the inverse mapping problem. So we could do a lot of these things with unsupervised learning without requiring a lot of data. And with that, I want to end with this story. Okay, so this is a recent paper, 2018 paper, where they were trying to play Atari game and trying to analyze the human priors. Okay, so the first frame shows the original game. Okay, and they let the humans to learn this game, and reinforcement learning agent to learn the game. And humans took about 4 minutes to learn this game, whereas reinforcement learning took probably an order of magnitude, or 2 orders of magnitude more than the reinforcement learning, more than humans. Okay? Then they started changing that game. They masked the semantics of the game, reversed the semantics, and then so from this, let's focus on this original game, the outcome of the original game. The reinforcement learning agent does not have any prior, right? It does not have any domain understanding. It tries things from randomly and try to learn, so that's why it is inefficient. Whereas the humans, we know the world, and we sort of like, okay, it's jumping, it's a block, and so on and so forth. So we bring a lot of domain knowledge into the game, and we can do better. And then they started changing the game in different ways, all the way up to changing the gravity. And what they found out is that the humans now take a lot of time to learn this game, to do well on this game. Okay? But the reinforcement learning agent took the same time as it took for the original game. Okay? So there are 2 ways to see this problem, to see this problem. So one, we need to bring a lot of domain knowledge into the reinforcement learning agents to deal with these type of things, because domain knowledge helps a lot. On the other hand, if we don't know something on this particular domain, it's better to let the reinforcement learning agent to do the experiments for you. Okay? So I think the best is to combine both of this. So what we know, we have to incorporate those domain knowledge into the reinforcement learning agent, and we have to let the reinforcement learning agent to explore things by itself as well. Okay, so thanks to my collaborators. I'm running out of time, but these are the collaborators, part of the projects that I presented, but there are a lot more very smart people. I benefit a lot from their collaboration, acknowledgements, starting from early career program to Argonne, LDRD, and SciDAC projects. And with that, I end my talk. Right. Thank you.
Take the prerogative of starting myself. I'm still trying to wrap my head around what exactly the neural networks are composed of. My analogy is, if we compare to the brain, of course, where all the neurons are identical. But you're starting out with the idea that the neurons are in some way different, and that they respond to different things. Is that correct?
So the neurons in the neural nets?
In the neural nets.
They are not smart by definition. So if you look at it more from the optimization perspective, what it is trying to do is to solve a very large nonlinear optimization. And we have, neural nets, you start with some random weights, and then you want to adjust those weights in such a way that you minimize your objective function, right? So it is not, so there is some sort of structure and there is some sort of hierarchy in the way that we build the neural nets. And this allows us to efficiently backpropagate the errors using the gradients. So
That feeds back to your weights.
yes, and then go and nudge the weights to minimize the loss. So the computational units in the neural nets, by definition, they are not smart, right? Like they are not intelligent and so on and so forth. These are like information processing unit. So whatever that comes before this layer, it takes, sums up, and then pass through a nonlinear activation function and send it to the next layer. So all it does is a bunch of matrix multiplications.
Okay.
And the way we use the matrix multiplications, it's the humans who design those algorithms in such a way that it can do really cool stuff. So I think I would still say the intelligence is, if you take supervised learning, the algorithms, the intelligence is on the human designer. But if you move to reinforcement learning, so take the game of Go, the AlphaGo, it beat the world champion, and some of the moves humans could not understand. They said they could not. It's impossible for humans to come up with such kind of strategy, and those strategies were sort of built by self-learning mechanism. Reinforcement. It started exploring by itself and tried to come up with strategies for winning and so on and so forth. So it's
effectively teaching humans.
Yeah. Yeah.
Those will show up in the next textbook.
Exactly. Yeah. So so it depends on which method we are talking about, yeah. So by definition, the neurons are not intelligent in convolutional neural nets and things like that.
Other questions? Okay.
Great presentation, thanks. You were showing, I thought, which was pretty cool, using an unsupervised approach to optimize the net architecture itself for a problem. For that problem, were you using, at the state values and ultimately at the end, were your optimization factors both time, computational time and accuracy, or what combination of those are you using ultimately to reward the system to get to its architecture that modeled the problem? In other words, you could have one architecture that would model it very, very accurately, but take 2 times the computational time, as an example.
Yeah.
So was computation time part of that optimization scheme?
So we didn't. That's an important question, right? So we didn't include that explicitly, but implicitly, as soon as the agent builds a network which is smaller, it can train faster, and it gets rewards from those type of networks much faster than really large networks, the agent that builds really large networks. And just by virtue of that, the agents start learning, okay, I need to build smaller architectures with high accuracy so that I can get more rewards. So in this case, it worked better, but there was another case, it's a robotics, they were trying to teach the robot to move quickly, and they didn't think about, or the one thing that showed is the robot started doing backflipping. Okay, so if you try to measure the distance between, okay, I start from here and I want to measure the the distance traveled as a sort of a feed distance, then probably doing the backflipping is the best strategy, and that's the thing that you don't want, right? So we have to really think about what type of reward function we want to give to the agents, and reward shaping is the key for the success of our reinforcement learning. So it's even the the DeepMind AlphaGo game. It's not like an undergrad came up with that algorithm. It's really smart people. They are hand selected, and they worked on it for 2 years to come up with the correct reward function that can beat the world champion. So reward function is something very, very crucial, and that is still manual.
Thank you.
Okay, let's see. Why don't we start with you? You're more accessible. And if you could pass the microphone back.
So let's suppose in 50 years that science has been taken over by machine learning, and we've developed a quantum gravity neural network that's able to predict high energy phenomena that are currently beyond us. Do you think it is a useful field to then try and break apart that neural network back into physical laws? Is that even a useful question to ask? Or does that mean that all science from then on will just be black boxes run by machine learning?
No, okay. So let me make, if I predict anything 50 years from now, that will be wrong. But that's the whole, if you are an advertising company, you are fine being a black box, right? You can build a model that is black box, you are good, and as long as your revenue increases, you are doing great. But in the science, it's not the case, right? So this is, in a sense, right now it's black box. There are a lot of efforts to make it as a white box, okay? And then you can think about reinforcement learning as a mechanism to generate hypotheses for scientists, right? So this is the data, and this is how our human knowledge, our human prior is based on. And I want the reinforcement learning agent to go and do experiment by itself that sort of incorporates its prior knowledge, but will be able to do exploration and then say, hey, this is a hypothesis I came up with, which is not in your prior. So I think those are the sort of the valuable things. Even so, there is something that we need to address on the black box side, but these tools will be beneficial for us in the context of design of experiments, hypothesis generation, and so on and so forth. So I would see this as more accelerating the scientific discovery rather than everything is going to be black box. So that's what I predict.
The group that we're in has, over the past couple of years, studied experimentally supervised learning. And we have the usual canonical example of I have a neural net, I show it pictures of cats, I show it pictures of dogs, and after a while it gets very good at telling the cat from the dog. And at that point I ask the annoying question, what if I show it a parrot? How does, in particular supervised learning, but in general, how do neural nets deal with novelty, with things they've never been trained on? Is there any way to deal with that?
So to address that problem, supervised learning may not be the perfect setting, although there is this idea of uncertainty quantification or probabilistic machine learning in which, so you have a set, training set, and training set is a subset, right, of what you potentially can see over the lifetime. And as soon as you are outside the training set, in this case, cat and dog, now you are giving parrot. So this is outside of your training set. At least your neural net should be able to tell you, okay, I cannot do this prediction, or my confidence in predicting this as a cat and dog is really, really small, right? So that will sort of allow you to say, okay, this is outside of my training data, and I need to do something about this. And related to that, there is also things called zero-shot learning, few-shot learning, and so on and so forth, which basically deals with the scenario that you mentioned. Okay, so I have some data, and now I give a new data that does not belong to my class. It's your goal to learn this within few samples, the new set of data, because your training data now is sort of going beyond the range that it is. But then you say, okay, the method says, okay, I'm not confident about predicting this, and then you say, okay, this is the label, and then you want the system to immediately learn that and be able to do predictions on the parrot in the next timestamp. So, those are the things that people are working on, and there is sort of new methods, zero-shot learning, few-shot learning, and so on and so forth. So there are different ways to attack this problem. There's no unique method to address that problem. That's what I think. Yeah.
I just wanted to comment that the irony of that question is that it's something humans aren't that good at either, and you can just witness such animal names as the hippopotamus, which it means river horse. So a hippopotamus to a person seeing it for the first time looks an awful lot like a horse. But perhaps with machine learning we could come up with some sort of measures for just how well things cluster a little bit more easily than with humans, and then see if something is abstractly novel rather than just saying whether it's probably one or the other.
Sure.
Okay. One last question? Okay, well, let's thank our speaker today.
Thank you.